Okay, next, let's talk about an acceleration-based steering law, right? We have a gimbal rate that we want to track. So that's our velocity-based steering law. This comes out of your classic VSCMG control. We generate this 3x2 NQ matrix. We've got this new ADA state, which is wheel speeds and gimbal angles. And then we find the minimum norm answer, a weighted minimum norm, depending on which modes we want to use and not use, right? So we can play with that. But in the end, we have gimbal rates. And we can't just say, Josh, move at 1 meter per second. Somehow we have to say, look, Josh, apply this force, this torque to make a mechanical system move, right? And we have that. That's the motor torque equation and the full equations of motion at gamma double dot. So we want to come up not just with gamma dot, but we want to come up with something that specifies what is your gimbal motor torque that you should produce such that you track this. And that's the acceleration-based steering law where we now, so this will be an inner servo loop. You have there's now multiple levels, right? We've got our MRP feedback, the outer loop that generates an LR. Within it, we have now the VSCMG steering, which will give you a omega dot that we can use to compute a motor torque for reaction wheel mode, but we get a gamma dot, and we can't use that directly. So now we need a loop within it that takes that gamma dot from the steering law and says, okay, that's my desired rate, 0.1 radians per second. I am moving at 0.02 radians per second, so do I torque up or down? How do I make it match? That's a loop within that loop that we have to do. So again, CMGs makes things more complicated. But this is what we'd like, that when your control says, I should be having these gimbal rates, because with these rates I generate this stuff. You want to make sure that if you're off to begin with, that you will be. Starting up, you're never at the right gimbal rates to start with. But once you get on that curve, you want to stay nice and close on that curve. And because your control will be a nice smooth function that says, okay. And when you don't have the right rates, your your outer loops will automatically compensate because it says, okay, I want this torque to move left. Now you only gave them a fraction of that torque. So next time it adjusts and goes, I still want a big torque, right? And it waits till you catch up, and then the outer loop and the inner loop will be in sync because then the whole thing will stabilize. Your overall stability guarantees were only there if you actually achieve this. And at the beginning, we don't have that stability. But since you will track in a finite time, we can still argue stability. There'll be some initial transients. You might actually wobble a little bit more just for a few seconds until your CMG catches up. And now we're tracking the complete history that we need. So sometimes too, when you turn on the control, instead of just turning on a PD control, wham, and go from 0 to torque, sometimes people put in Bezier curves or a low-pass filter that kind of smooths out the torque profile and automatically gives you kind of a smoother ramp up to the torque and go. But it's the same issue. You're not creating the torque that your math says you should have for initial startup period, but you're trying to smoothly get onto that curve. All right? So those are considerations, and you're doing this in your homework. So just at the stage when you get to the CMG servo, you do this before you get to the outer loops because you need this working. You have to start from the innermost loop first and then build up the one that tracks your wheel speeds, the one that tracks your gimbal rates. You put in nice and slow gimbal rate histories on the order of 30, 60 seconds. Don't do really fast stuff because that's what your outer control will require. Something that changes on the order of tens of seconds to minutes. That's the kind of slow profile. Then you can just prescribe a sinusoidal. Gimbal 1, I want you just to go through a slow rate of 0.01 radians per second, oscillating every 40 seconds or something. Your spacecraft will do weird things, that's fine. Just make sure that you actually get on my desired rates and those two curves should start to match with what you've generated, okay? So inertial terms, Ostwald exploiting. Yep, so how does this work? We've already done a reaction wheel servo loop by hand earlier, right? We showed that you can get this and you can run this at a high frequency. So every update you get an updated, what's the desired rate out of this control. You can run this at 2 hertz, 5 hertz, whatever you want to do. So that part we have. What we want to talk about now is the gimbal rate stuff. And it's very, very similar, right? Because we have gimbal rates. What we need to figure out is what gimbal accelerations, thus motor torques, accelerations will relate to motor torques, are required to make gamma dot track our desired. But gamma dot desired comes out of this weighted minimum norm inverse you've done. Make sense? So there's a loop within a loop. So if we do this, this is what has to go to 0. We will generate our favorite Lyapunov function, which is basically x squared over 2. But here, instead of x, I have delta gamma dot. Delta is the tracking errors in gimbal rates squared over 2. And that's our Lyapunov function. Then we differentiate it, which will give you delta gamma dot times, that should have been a big delta, gamma double dots, and gamma, and then we prescribe it to be this function. Is this negative definite or negative semi-definite? It's like, oh God, I thought we left that 3 weeks ago. So Paul, you're laughing, so I'll just ping you. What do you think? Negative definite, negative semi-definite? Negative definite, I agree. The function only depends on delta gamma dot. I don't care about the gammas. I'm not prescribing the gimbal has to be 30 or 60 degrees. I'm just saying the gimbal should be 1 degree per second rotating left, or positive, negative. That's all. So this is actually negative definite. That's why in the earlier homeworks we had several examples of simple x dot equal to 5 minus x, first order dynamics, because all these servos tend to be first order differential equations. You can plug in, you can specify something negative definite for them. Don't need Mukherjee-Chen. We can directly get something that we can argue asymptotic stability. So if you do this equal to this, again, we can factor out rates and then set those equal. And from this, you can back solve, because the delta gamma double dot will have gamma double dot minus the desired gamma double dot. And you solve for the gimbal acceleration. Cool. So now we come up with the acceleration we should have. So it's the actual rate minus your desired rate. And if you hit this, then this goes to 0. So that's good. That means you're on the curve. But the curve is not necessarily constant, right? The curve may go up and down. So the other part is we're feed forward compensating for the desired gimbal angular acceleration. And how do we get that one? Because our control up here only computes gimbaled rates, desired gimbal rates. And my suggestion is you can probably just do simple numerical differencing. This is an inner loop. It have gain. High gain is disturbance rejecting. You just need even a decent estimate of, you need kind of 0.1 radians per second squared right now on what we're doing in our stuff. So you can simply take your current desired one, keep track of one last time step ago, and then do a numerical difference, and you'll have a pretty good estimate of that. But this is something you can play with. So you're doing this in your simulation, right? This is something that you have, and you can just put a proportional feedback on it if you wanted to, or the proportional plus feed forward will let you not update quite as often. So I would recommend looking at that, but you can play. There's many ways you can make a servo loop and to make it robust. But just make sure you put in, don't put in a 50 hertz signal as a reference. Put in something that's like, 0.002, It takes 50 seconds to finish a loop. It should be slow and smooth. Because also with the references, we were assuming our gamma accelerations are negligible, right? We dropped the b times that as being really small. So there is some unmodeled dynamics. And we want to make sure that is a good assumption, right? So when you're testing it, that's what you do. So gamma double dot, that doesn't give me motor torques. How do we get motor torques out of this? Not quite. Not F equals ma. What do we use here for gamma double dot? Let me see. CMG motor torque. We have the motor torque equations. So it's not just inertia about the gimbal axis times gimbal accelerations equal to the motor torque. You could do that as a first cut, and then you're just relying on that feedback term to make it robust. It won't track quite as perfectly, but you got that. But here, these are all terms we know, so you can certainly throw them in. If this is the acceleration, but we actually got these gyroscopics happening and these gyroscopics happening, you can compensate and you will get a more accurate prediction. To have this gimbal acceleration at this instant, this is what we have to do. What's the troublemaker? Do we have acceleration? No?
You do if you ran your
Well, but look at it this way. Now, again, some people just drop it. Absolutely possible. And you're counting on the feedback to stabilize, because this is maybe, sometimes adding all the truth is good, but it also can be very expensive. You might have to estimate it. It might be more math. Or if it comes from sensors that are noisy, sometimes adding these extra terms to be extra rigorous actually hurts you, because you're adding more noisy stuff that versus ignoring it causes less problems. So it's a little bit of a trade-off. But we have this equation. If we have this gamma, because this has all come together, if we had that gamma acceleration that we're looking for, and the torque, and this wheel acceleration, and everything comes together, if we produced all this perfectly, this is the angular acceleration that the spacecraft should be experiencing. So you could do that. Or you could take your actual rates, and actual rates from a second or last time step, and do numerical difference and go, okay, that's good enough. But then again, with rates, numerical differencing, the rate gyros, especially some people are flying MEMS, these smartphone, really micro rate gyros. What's the big problem with them? A lot of noise, right? So if you take really small time steps and you're just differentiating that, you might be throwing in just basically rubbish. It's hugely dominated by noise, and with differentiating on small time steps, so you might have to have a smooth differentiation, and it's just a whole other can of worms. Or you can ignore it and just pick a bigger K gain that we had earlier, right? Yes, Henry?
Just to make a comment, that wasn't actually a good model of your dynamics.
Then you're off. But this is a pretty good model of your stuff. You should know most of these states, and including if you have some external disturbance, you could include that as well. If you know what your SRP is going to be, the control's already taking advantage of it. So the control already computes the L, if you have it.
Maybe don't know the actual.
No, then you have unmodeled stuff. That's always there. But that's also true with just an MRP feedback or any other controls that you do. So anyway, just wanted to highlight, so when you get these gamma double dots, right, that we did here, flipping through all of this, yay. I know there's a faster way to get there, but that's fine. This is kind of fun. Bloody hell. Okay, so if we do all of this, we get this steering law. We will get convergence, but as you can see, there's lots of design decisions that we have. This just gives you the gamma accelerations. And at the most basic, you could say UG is equal to JG times gamma double dot. It's kind of there, but you got other terms. And the more information you can include, you will find it might help. If you use that, the acceleration term is the trickiest one. I think many people just drop that because we tend to be rotating very slowly, and the spacecraft angular accelerations tend to be quite small compared to all these other gimbal accelerations. So that's a really small term to begin with. So just dropping it and counting on this loop to be stiff enough with a decent gain. So you want to pick a gain to maybe get there within a few seconds. You don't have to get there within microseconds, because then you have huge gamma double dots, which is something we're ignoring. But get there within a few seconds, and then you should be following it reasonably closely. Then your VSCMG control has a chance to actually work and give us what we need. Okay? Good. What do we have? Oh, just 2 minutes left, or a minute and a half. Okay. No, so essentially at this point, we've derived this control. We have the VSCMG, but you get wheel accelerations and gimbal rates, so you will have to still have a wheel torque loop that you can generate that'll track this. That's pretty straightforward. Or you can just use the wheel motor torque equations, because if we have those, US was JS times big omega dot plus this angular acceleration. Again, that's a really small term. People tend to drop that. So you could just map from the wheel accelerations to the motor torque in an open loop way without even a feedback tracking. That's what most people do. The outer loop, if you don't track that wheel speed just right, the outer loop will actually help stabilize this again. And go, okay, we're off just a smidgen, I'm going to adjust my next control, and the whole thing works. But it's the gimbal one that's a little bit more involved. You want at least this term. You might include this, and when you put this into the motor torque, you can play with which terms to include or not, and kind of get a feel for that. Okay?